Hello, everyone. Let's try to do this homework problem here where we're going to use polar coordinates to find the volume of the given solid. And this is a double integral. So we have our double integral and we're going to use polar coordinates in our double integral. The first challenge, I guess, would be to sketch the graph. So let's check that out. Right, so we have a cone and a sphere. So let's see about that and how well we can, or how easily we can sketch that graph. The sphere, I think, is a little easier if you know that the equation of a sphere is x squared plus y squared plus z squared equals r squared. So the radius of this sphere would be r. You might use a different letter besides r, but anyway. So that's a sphere centered at the origin, and so it has 1 is the radius of that sphere, and okay, I'll draw that. So that's our sphere. I could use a different color or something, but that's a sphere, and then this part maybe is a little bit less straightforward to everybody, but it's anyway. We should know this after a while. But maybe this is new right now. But for z equals radical x squared plus y squared, if you square both sides, you see z squared equals x squared plus y squared. And this is one of the things we've studied, which is a sphere. But see, because it's z equals the square root, it's only the top part of the sphere. So for this class, a sphere means what I'm drawing here. I'm going to erase that because it's only the top part. But this is what we've learned as a sphere. But a cone. This is what we've learned as a cone. But because it's the square root, it's the top part, which is more like generally what we think of cone anyway. It's just the top part. Okay, so I'm drawing that. Anyway, so what the problem is asking us for is the area between the sphere and the cone, and that's just this part right here. I'm sorry, the volume. We're trying to find that volume. So, all right. So what we're going to do to find the volume is we're going to integrate over a region D the difference between two functions where one function is on the top and the other function is on the bottom. All right, and so it's now that we have our picture, we can find, we see what's on the top and which one's on the bottom. So, and by the way, well, what's D? Let's just talk about that for a moment before we keep moving ahead. So, all right, D is a region on the XY plane, and the way we view that region or find that region is we project this solid onto the XY plane, and it's a little bit, we just have to sort of just look at this and see that the projection of the solid onto the XY plane is going to be a disk. So we can see that the projection is going to be this top. I mean, the projection is taken from this top part here, and all right. So that's what D is. Okay, so that I brought that up right now because I have D here. So let me just go back to writing down this volume formula. So then we'll find D. So it's a double integral over D of the top function, and we can see that the top function is this sphere, and I can make it a little darker, a little bolder, but it's this sphere. And that's the part on the top of our cone. So it's like a, it's like an ice cream cone with ice cream in it. So here we have, just going over here. So here I have z squared equals 1 minus x squared minus y squared. Let me write more neatly. Z squared equals 1 minus x squared minus y squared. We'll want to solve for z, and I'll take the square root. Usually I'll do plus or minus. However, since I know I'm only looking at the top part of the sphere, the upper sphere, then I'm not going to do plus or minus. So I'll just do that. So that's the top part here. So I have radical 1 minus x squared minus y squared. And then I subtract the cone, and the cone is this part right here. So so I have subtracting radical x squared plus y squared, and all of that would be dA. Now let's go over and look at D here, this region D in the xy plane, which is a disk. And how do I know it's a disk? Well, I have that by looking at it, but I'm going to determine that also algebraically. But the key here, or the question really becomes, is, well, what's the radius of that disk? So the boundary of D is determined by the intersection of the cone and the sphere. So this boundary of this disk is going to be determined by the intersection of the cone and the sphere. So let's find that intersection. See, you can see where they intersect is this part that I'm highlighting right here. So let's find those by setting these two equations equal to each other. So for intersection, I have, write down a little more than I need to, but I'm going to write down cone equals z equals radical. Well, okay, hold on. Yeah, the radical's okay, but look. Why don't I use the z squared for the cone? Okay. Well, either way. Okay, so I'm going to have z equals radical x squared plus y squared. In the sphere, I have z squared equals 1 minus x squared minus y squared. So I guess I'll square both sides here, and I'll have z squared equals x squared plus y squared. And putting those together, it's equating, I'll have x squared plus y squared equals 1 minus x squared plus minus y squared. And then I bring both to the other side, and I then factor out. So x squared plus y squared is equal to 1/2. So this is a circle, and the radius is not 1/2. Radius is 1/2. When I say circle, it's centered at the origin. But, this is the same thing as r squared equals 1/2. If I use the identity that x squared plus y squared equals r squared, which is an identity from polar coordinates. And that means that r is equal to the square root of that. I'll only do the positive root. So that's a way to describe this circle, is r equals 1/2, and that leads to our description of D. I'll put in set notation. D is r theta, such that, well, it's a circle, so for circle we have theta starts at 0, and we go all the way around with theta, and that takes us to 2 pi. And then r starts at r equals 0, which is the origin or the pole, all the way up to r equals 1/2. So we're getting there. So now I'm going to cut and paste this volume expression and copy and paste, I suppose. And okay, So here we go. So volume is going to be this double integral, and I'm going to integrate, sorry, I didn't want to put that bar there. I'm going to integrate first with respect to theta, 0 to 2 pi, that'll be d theta. And then with respect to r, and r will go from 0 to 1 over square root of 2. And now I'll write down the difference of these functions. But I'm going to use again that x squared plus y squared is r squared. And over here, I have 1 minus x squared minus y squared. So that's going to make 1 minus r squared. So I'll have square root of 1 minus r squared minus square root of r squared. And sort of not sure what I was intending with those parentheses. All right. So then in terms of for that other piece, here's dA, I'm integrating d theta, but don't forget for r, I have to write dr d theta. So this is dA, one of the big things that I forget. I mean, I shouldn't. I haven't done it in a while. Every once in a while I forget to put that r there. Definitely we want that r when we integrate in polar coordinates. And all right, I will just do a quick one here, is that this expression here has no theta at all in it. So that means I can integrate the theta separately. This is going to be some number, I'll determine that later, inside the integral d theta. So I can just take that number out and I'll just integrate that separately. So I'm going to calculate that. That's an easy one. And then I'm going to multiply r throughout here. R radical 1 minus r squared minus r times radical r squared dr. Okay, so the integral of d theta is, well, okay, if you have a constant and you integrate a constant, the integral is the constant times the length of the interval. I'll write this all out, but I don't think I should have to. But anyway, I go 0 to 2 pi, so that's going to be 2 pi minus 0, which is 2 pi. So as I said, a faster way is just to take the 1 and multiply by 2 pi minus 0. So I do that quite a bit because there's so much integration. And so if I see something, then I'll do that. You know, that makes it a little quicker. It's not just a cheap trick. This is a theorem that's stated in the single variable calculus part of the textbook. So I have, this is equal to 2 pi times the integral from 0 to 1 over rad 2. And I'm going to rewrite the square root as a radical expression. And then, okay, we're assuming that r is positive, so that the square root of r squared is equal to r right there. If it's not positive, we have to do the absolute value. I have to write the absolute value. And then here's another piece, is what I'm going to do is separately, I'm going to work out this indefinite integral right there. So I'm just going to do that on the side of the paper, and it's always for everyone, there are issues of just having it look nice and organized. So that's not too bad, but I'm going to go ahead and show all the work and use substitution. It's true when I'm doing this problem on my own, I just sort of, I sometimes just guess and check. I guess, but then I have to check. And I do that to find the integral. But anyway, r dr, see, look, so this is a very standard classic substitution problem where I have a function raised to the 1/2 power. So this function is u equals 1 minus r squared, and we differentiate, and I have du equals negative 2 r dr. I only divide by the negative 2. So r dr is negative 1/2 du. So I have negative 1/2 integral du of u to the 1/2. So it's not totally fall apart and become too messy. But this is then negative 1/2 u to the 3/2 over 3/2 plus c I'm always wondering, should I keep the c there? I'm using this as a definite integral, but okay. So I divide by 3/2, which is multiplied by 2/3, and then u is 1 minus r squared to the 3/2. And so this becomes negative 1/3, 1 minus r squared to the 3/2 plus c. The thing is, if you do these, and this is such a commonly done use substitution, you can sort of guess what the answer is going to be and sort of fiddle around with this constant. See, because the derivative of r squared is 2r, so you see that there. So it's mostly just getting that constant right. But, okay, and then, well, I might as well, maybe I'll do this on the side of paper too, is that of course, the integral of r squared dr is we know that one more easily. It's an easier one. Maybe I'll call that C, I don't know, C2, a different C. Okay, so we get, this is equal to 2 pi, and I have negative 1/3, 1 minus r squared to the 3/2 minus 1/3 r to the third, and we're evaluating from 0 to 1 over rad 2. Be careful in this situation when I plug in 0, not everything's 0. R to the third when I plug in 0, 0, but for this part, 1 minus r squared plugging in 0 does not give us 0. So sometimes I just sort of throw away that 0 bound, but in this case, not. I'm not going to do that. All right, so I'm just going to put the top bound first in and then subtract the bottom bound. So I have 1 minus 1 over square root of 2 squared, all raised to the 3/2 power, minus 1/3, 1 over square root of 2 to the third power. And then I'll subtract 2 pi, negative 1/3, 1 minus 0 squared to the 3/2 power, minus 1/3, 0 to the third power. Yeah, it's looking decent, but then at the very end I ran out of space and I decided to be sort of messy. Okay, so this is 2 pi, negative 1/3. All right, so, okay, let's take each step. Let's not rush, but the square root of 1 is 1, the square root of 2, no, 1 squared is 1, the square root of 2 squared is 2. So this gives 1/2. And then a little bit of a trick to this, I think, is I'm going to write this square root of 2 as 2 to the 1/2. And then I have minus 2 pi times 1/3. Okay, so this is 2 pi. I'm just taking my time, really. Negative 1/3, 1 minus 1/2 is 1/2 to the 3/2 power. And then I dropped by mistake there. There's a 3, it's supposed to be a 3 here. So this is going to be, all right, so we multiply the 1/2 times the 3. That's how we raise something to a power. So this is also 1/2 to the 3 times 1/2, 3/2. So I'm going to write it that way so I match this. So I see those expressions are the same. Minus 2 pi over 3. I was sort of hesitant how I'm going to write that. But, okay, so let's just keep going. 2 pi. And I have the same expressions twice with a minus. So this is going to be minus 2/3 times 1/2 to the 3/2. I'm going to rationalize denominators and all that stuff in a bit. All right, now, what am I going to do? Well, all right, let me just keep moving ahead on this. Okay, so now I'm going to start rationalizing denominators. This 1/2 to the 2/3 power, 1/2 to the 3/2 power, I'm going to work on that one. So if you don't remember this, but I think you do, that 2 to the 3/2 is the same thing as 2 to the 1 power times 2 to the 1/2 power, which is 2 rad 2. So this is 2 pi times, oops, I guess I'm getting flustered or something. Okay, so this is that times negative 2/3, and then I'm going to divide by 1 over 2 rad 2 minus 2/3 pi. And then we see there's a little canceling. These cancel. I guess I dropped a negative in my heavy concentration of doing some of these things. I dropped this negative. And one of the reasons I'm like, oh yeah, something's not right there is because this is a volume. So we definitely are not going to get a negative for volume, right? I mean, how can volume be negative? So I see I had negative 1/3 there, and I just, by carelessness, not focusing well, not concentrating well enough, I threw that away. So yeah, I have to really pay attention to these problems. Okay, so we have 2 pi, it's negative over 3 times 1 over radical 2. Okay, hold on. Let's just keep working on this. Okay, 2 pi times negative 1/3. 1 over rad 2 is rad 2 over 2 plus 2/3 pi. So these guys cancel out. I'm trying to match the answer in the book. Anyway, so now I can factor out pi over 3. And then I'm left with 2 minus the square root of 2. That is the answer in the back of the textbook. So there we go. Okay, and it's a positive number. 2 is greater than the square root of 2, so 2 minus radical 2 is positive. And that was sort of a lot. But I really think, I showed quite a few steps. And if you didn't show all the steps, you could, I guess, write this all much quicker. All right, well, I misspoke and I made a few mistakes. The big one was forgetting that negative, but finally got the job done. Okay, thank you. Goodbye.